So good afternoon, everyone. So it's my pleasure to introduce today's speaker from our AS, Professor Yang and Shala Song. Okay, so before we get started, let me briefly introduce you, Professor Yang Shala Song. Professor Yang Shala Song, the ordinary professor at École Polytechnique and École Nationale de Passion in France. Hopefully my pronunciation is correct. Okay. He's a distinguished figure in the field of continuum mechanics. He also holds the positions of chair professor at large and a visiting distinguished professor at City University of Hong Kong from 2011 to 2016. He's currently a senior fellow of Hong Kong IAS. During his career, he served as president of French Academy of Sciences in 2009 and 2010, and presides over the Institut de France in 2009. Professor Shala is a member of the French Academy of Technologies and Academia Europaea, and holds foreign memberships in several famous renowned institutes I think it's in Italy and also in Portugal. He's also honorary member of the Hungarian Academy of Sciences and a corresponding member of, I think this is it's hard for me to pronounce the name, okay, so it's an academy in France with a vast body of work that includes over 190 publications, 12 books, textbooks, and 8 multimedia software. Professor Shala Song is a renowned global leader in the field of continuum mechanics, contributing significantly to both theory and its practical applications. I took the course of continuum mechanics about 20, 25, 30 years ago when I was a student at Princeton. I think I still like continuum mechanics. Now today, I think today's topic is about Tresca's memoir. Usually we pronounce it Tresca when I taught students, okay, it's a Tresca criterion, but it turns out that it's a Tresca because this person from France. On the fluidity of solids, the birth and history of the mathematical theory of plasticity. So let's give a round of applause to Professor Shala Song, okay?
Well, thank you so much for this introduction. The problem, is with such laudatory comments, afterwards you have to meet the challenge. So it's up to me to meet the challenge. So here we are. Let me first say a few words about what I would call the genesis of the lecture. Where does this lecture come from? Well, this is an aphorism by a British mathematician. Young men should prove theorems, old men should write books. Obviously, I belong to the second line. You agree, not the first line. So I took it to the letter. And as you have been told, I've been teaching here for 5 years, from 2011 to 2016. And at that time, and afterwards, I started writing a series of textbooks. These two ones here, first ones were what I was teaching here. And those ones could have been lectures I would have given here also. I also wrote one in Spanish. Well, as I understood that those books were the last one I would write, I took great care in double-checking any reference. So it happened that for that very book here, I had to introduce Tresca's criterion. Tresca's criterion, this is a shape, about Tresca's criterion. And so I wanted to go to the reference, the original reference. So that is what I did. And I found not only one reference, but all these references from 1864 to 1871. Those in blue are memoirs, and those in black are short abstracts that were published in the proceedings of the Academy. So it's not only one reference, but so many references as these ones. About this one, Kuiter, maybe you heard of this guy. Kuiter, he was a Dutch scholar in mechanics. He wrote, Tresca's paper on the flow of solids may appropriately be regarded as the birth of a mathematical theory of plasticity. So my talk today will be about Tresca's memoirs on the fluidity of solids, with the title The Birth and the History of the Mathematical Theory of Plasticity. Well, first a few words about this guy, Tresca. Tresca is Italian. It's an Italian word, name. This one was the son of an Italian immigrant to France. 1814, 1885. He was elected a member of the Academy of Sciences in 1872. He graduated in École Polytechnique, established 1794, and École des Ponts et Chaussées, which is a civil engineering school, established 1747. It is the oldest engineering school in France and the oldest civil engineering school in the world, as recognized by the ASCE in the US. After graduating, he worked as an engineer, and after he became a professor of applied mechanics in two schools. First, École Centrale des Arts et Manufactures, established 1829, and Conservatoire des Arts et Métiers, established at the very same time as École Polytechnique. And it is there that he was in charge of a laboratory dedicated to industrial mechanics. There he carried out his experiments, and also he realized this famous X-shaped standard meter. It was a global reference for years and years and years. So this is about Tresca himself. So we're starting with the birth and then the history. First, the birth. The birth, Tresca's memoir. As I said, many memoirs, where they came, which we have to look at the scientific context. What was at that time? What did we do? What did we know? Filling a gap between this one, Coulomb. I think 1 year and a half ago, I gave a talk here about this. Coulomb was only on stability analysis, based upon the resistance of the constituent, not taking care about material behavior. He was not dealing with material behavior. So this is one. And at the other end of the gap is Cauchy. Word of Cauchy, elasticity, reversible behavior of materials described through the mathematical theory of elasticity. So in between, not as regards the years, but what is necessary to do. These two were very efficient for civil and construction engineering issues, but for forming materials, it was not. You could not form material based either stability analysis or elasticity. Something was missing. You had to know the behavior of materials to know how to make forming or metal processing. So 6 memoirs addressed to the Academy from 1864 to 1871. 6, here they are. And in those memoirs, Tresca has described and reported with the utmost precision all the experiments he did. He did experiments on lead. This is what is most famous. People refer to the experiments on lead and believe there were only experiments on lead. But no, many other materials. Lead, tin, copper, silver, steel. It's not finished. Modeling wax, porcelain clay, ceramic clay, brick clay, all those materially tested. He tested and tested all these years. So what were the results of this test? The results first were that he discovered 3 stages in the behavior of materials, distinguished 3 stages. The first stage was already perfectly known, perfect elasticity. He says, perfect elasticity, you have linear relationship between what he calls the forces developed between molecules. What he called molecules, we could call particles, material particles. The forces between material particles are a linear relationship between those forces and the relative displacement between particles. So you know this, it's linear elasticity. Then in perfect elasticity, nonlinear relationship partly permanent deformation. But he was not interested in that. He was interested in the last one, fluidity of matter. Here it is. I translated, of course. Beyond this limit, we consider that the state of fluidity of materials, that you have material which is subjected to very high pressure, so it becomes fluid, it can flow. And in that case, he says the forces that are developed are absolutely constant and can be, forces between neighboring particles are absolutely constant and can be evaluated by means of a resistance coefficient, which he calls the fluidity pressure. So one constant he has to determine. It's exactly what you know, what you have learned with Tresca's criterion. Here it is. So this is what is known usually as Tresca's result. It is fluidity with forces, constant forces. Okay, it is what we know. But there is something in addition, which usually people do not refer to. Tresca also is concerned with material flow. And he says, well, we have shown that matter can flow and that the direction of flow is subjected to geometric conditions. He knew that. And beyond that, preservation of primitive density, constancy of the total volume. All this he has observed and described and recorded. So this means that we have something like a flow rule. So now something happens at Saint-Venant. Maybe you heard about Saint-Venant, sometimes in elasticity, also maybe in fluid mechanics. Saint-Venant is known for all this. Well, here appears Saint-Venant. Why? Let us look at Saint-Venant. You know he's dressed as an academician here. Why? Because Tresca was sending his memoir to the Academy, but he was not a member of the Academy. So his memoir could not be accepted unless the commission had reviewed them and accepted them. And Saint-Venant was one of the commissioners in charge. So he examined all those memoirs by Tresca. And in 1870, Saint-Venant presented, and of course it was accepted since he was a member, a note in the proceedings of the Academy. And he was referring to all the works Tresca had already presented. Here, I have to take my both hands. Here he refers to Tresca, 1864, 1870. And this is a title, very explicit title of this note on the equation of internal moduli, beyond the limits where elasticity could bring them back to their initial state. Beyond, that means when you have permanent deformation. But exactly. And what he does in this note, it is only to derive equations. We were speaking about deriving equations before. He derives 5 equations. But we know this equation. Here you see what he says. He doesn't use Coriolis notation, which is the notation we use now. But he uses Lamé. You know Lamé, this one is Lamé. Lamé notation, the notation we do not use any longer. Okay. And there are equations. You know these equations, the first 2 ones are dynamics equations. Volume invariance, Tresca's criterion, coaxiality. 5 equations. And he gave a name to this, hydrostereodynamics or plasticodynamics. Plasticodynamics is more or less, one you would say, the dynamics of plastic materials. Plasticodynamics. This was the first time this behavior was being named. Here are the equations. So with volume invariance and coaxiality, we have what we call now a flow rule, plastic flow rule. So at the end of this, it will be the end of the birth process, if I may say so, the cornerstones of plastic modeling, which are yield criterion, plastic flow rule, were laid down for the first time by those 2 people. This one is dressed as academician, but after he has been elected, of course, Well, finish with the birth, going to the history. And in the history, we'll see two different issues. First, we start with the yield criterion issue, and then with the flow rule issue. And afterwards, we mix all that. Well, the yield criterion issue, first thing is an energy viewpoint. So when you are looking at the history of mechanics, solid mechanics, it is always good to refer to Timoshenko. This book by Timoshenko is very interesting. And in this book by Timoshenko, you find something amazing. He says that as early as 1856, that is before Tresca's experiments, Maxwell is supposed, according to Timoshenko, he says he did, send a letter to Lord Kelvin saying, I have strong reasons for believing that when the strain energy of distortion reaches a certain limit, then the element will begin to give way. In other words, he was already aware that there should be some kind of a criterion, which he saw as the strain energy of distortion, that would decide about something like the flow of material. But nothing came out of that. Lord Kelvin didn't do anything with this. The first to do something like with an energy viewpoint was Beltrami. Maybe you heard about Beltrami in elasticity. His name is attached to some equations in elasticity. A famous Italian mechanicist and mathematician, in fact. But he proposed a criterion, but not distortion, but the total linear elastic energy can be retained as a criterion with critical energy estimated from a traction test. Okay, but there is a problem. This criterion does not account for an experimental evidence that is insensitivity of ductile materials to the hydrostatic part of the stress tensor. If you take the total linear elastic energy, you are sensitive to the hydrostatic part, so it doesn't work. And so I will go back and say what I wish to say now afterwards. So this doesn't work. And it comes to Huber. This Huber was a Pole, that's from Poland. The specific shear strain work, clear, specific shear, distortion, strain work as criterion of material strength. This was the right idea. It took the right point. It was in 1904, and you find an English translation in 2004 here. But in fact, it was with von Mises that this criterion was finally written, and it is usually considered as Huber, von Mises, or von Mises criterion. The deviatoric, and not the total, the deviatoric, the distortion, linear elastic energy will be retained as a criterion, and you will find critical energy not by a tension test, but by a shear test. Here it is. Sigma something are the principal stresses, you know. All these materials are supposed to be isotropic. Here. Now, let us go to the flow rule issue. I said we would consider both issues, yield criterion and flow rule. Flow rule issue, here we are. But we have seen that in Saint-Venant's note, the flow rule issue has already been addressed. Let us recall, here we were. Flow rule issue was here. But in these equations, these 5 equations, one equation, a 6th equation is missing, which Saint-Venant did not write. It is what we know as the consistency equation. It means that if you want to have flow of the material, you must have the yield criterion, which is saturated, but also you must stay at that point. So this equation says that derivative of the yield criterion with respect to time is 0. You must stay at the boundary of the yield surface. So we have these 5 equations plus 1 equation. We've got 6 equations. And now, about the flow rule issue, this is a quotation for somebody we will meet afterwards, who is Rodney Hill. Rodney Hill, in a paper in 1948, refers to von Mises' 1928, that is 20 years before, and say that von Mises introduced the fruitful concept of a plastic potential. This is von Mises' idea. What does it mean? Before saying what it means, I want to have those 4 names. Hill, we will see him again. Von Mises, and Hilda Geiringer. She's a lady. She's a lady, very brilliant mathematician. I think she was from Austrian origin. She had some problems because she was a Jew, as von Mises himself. And she had some problems, but she was closely connected with von Mises. By the way, she married von Mises in 40-something. Here they are. Richard von Mises, Hilda Geiringer, Rodney Hill. So let's go back. Now, criterion. Von Mises, let's say, call it von Mises criterion. A plastic potential. This part, we call it, the loading function or the yield function, as you like. This part is the plastic potential. That is what von Mises states is the theory of a plastic potential. What does it mean? Well, it means that the plastic strain rate, which is here, is an outward normal to the surface, the yield surface, which is F equals 0. So you write this. This is the flow rule. And you shall also write the consistency equation, which says that you should stay on the boundary of this surface. Well, so far, so good. It's okay. Yes, for me, this criterion, the normal, there is no problem. This is very clear. Well, what happens if you have Tresca's criterion? It's okay. When you are on the face, you see, on the facet of the criterion, there is no problem. There's an outward normal. Everything works properly. But if you are at an edge between 2 faces, what can you write? The gradient is not defined. Outward normal, what is it? How can you write the consistency equation? So we need something else to define the flow rule. And this is what Hill did in that very paper. He introduced an alternative presentation, the principle of maximum plastic work, which means that the work by the plastic strain rate in the actual stress state is greater or equal to the work by the same plastic strain rate in any stress state that is plastically admissible. So that is how he states this principle of maximum plastic work. Of course, it is compatible with what had been said before with potential, plastic potential, but it says more. It says that the criterion shall be a convex function of sigma, and that the flow rule will be an outward normal to the surface. And so when we have an edge, you have many outward normal, but it can be any of them. So here we are, you have such a point as that one. You have convex cone of outward normals, and dP belongs to that convex cone. This is what comes out of Hill's principle. So it solves everything. You see, here we are with Tresca's criterion, it works perfectly. But something that does not appear is what shall we say about the consistency equation? Well, the answer comes with Kuiter. Kuiter, a Dutch scholar, 1953, Kuiter says, well, if you imagine that you have a yield surface like Tresca's, which is the intersection of convex yield surfaces, if you have the edge here, so it gives the answer. So I say this, f is a sigma, is a convex function, then either you will be, if you are in a face, you know how it works. If you are at an edge, like that, this means that dp is part of the convex cone, and the consistency equation says that the plastic strain rate is a convex combination of the gradients of the activated elementary plastic potential. So you are at an edge like that one. So you have one normal, the other normal, and plastic strain rate is a convex combination of those two gradients. Well, one consequence of this theory is an orthogonality relationship, which had been already proposed by somebody else, Drucker. Maybe you heard about Drucker. Drucker had proposed this equality as a postulate, which he named quasi-thermodynamical postulate. This was Drucker's postulate, 1951. We were in 1953 before. This is. Well, so we have this one had appeared before. We will say something more about this postulate. Now, this is by, we say, 51, 53. We go to 1960s. Why convexity? Convex analysis. We have met convexity. We said that F should be a convex function. We have met normality. Convexity, normality, this makes us think of convex analysis. Convex analysis, this was already, in my opinion, in this paper, it's not a paper, it's a little booklet. It's a little booklet by Prager. The idea of convexity was already present, of convex analysis, but it was not in the mood of at that time, you know. The basic concepts had not been laid down. They came afterwards in 1960s by Moreau. This is Jean-Jacques Moreau. In fact, you can find them in this book, 2003, but he presented him in the 60s. Introduced concepts like subgradient, subdifferential of a convex function, and the support function. All those terms were new at the time, new concepts. This is just to explain for those who like, but it is not important to describe what it means. What I would say that with these concepts, we can write first the convex cone of outward normals is generated from the subdifferential. So the concept of a subdifferential by Moreau makes it possible to describe the convex cone of outward normals. So the plastic flow rule will be explicited with this theory, plastic flow rule. And also, it will be possible to write the consistency equation. But as a consequence, you do not get Drucker's postulate. It's inferior or equal to, not equal. So you see a slight difference with Kuiter's theory. At the beginning, you may think it's the same thing, but it is not the same thing. Here it comes. But not so important. As I was speaking about Drucker's postulate, let us say a few words more about it. Well, this is progressing in time. We were in the 60s. Now we are 70s, published in 70s. This guy, I'm Brezis, functionalizes Brezis results about the solution of quasi-static elastoplastic processes. So how you solve those problems. And what he established is this. The solution, if you have such a problem, a solution, stress rate, and plastic stress rate field, they do satisfy this equality. So Drucker's postulate is no longer a postulate. You don't have to impose it as in the consecutive equation. It comes out, it is an outcome of the solution process. So you see, we are progressing as long as we introduce new mathematical concepts, we are progressing. And there is something we didn't speak about, is work hardening. Tresca didn't care about work hardening. Remember, 3 stages. The second stage, he was not interested in the second stage, but he said, the state of fluidity obviously follows the period of imperfect elasticity, imperfect, characterized by a change partly permanent in the left of the compressed fibers. So not only you have a nonlinear relationship, but you have a partly permanent deformation. It is exactly what we call work hardening elastoplastic behavior. Exactly that. He had observed that he was not interested in that point. So work hardening, whatever it is, what is it? Well, the first scholar, first scientist whose name is attached to hardening is Bauschinger. That's a German guy. And it was as early as 1881. His name is attached to one effect called Bauschinger effect. Maybe you heard about Bauschinger effect. For instance, when you have a one-parameter loading process, let us say traction compression. This is traction. I should go back, my dear. Go back. Okay, here we are. Here you are. You have the elastic domain, traction compression. Let us say, let me go beyond this level. And then you unload the specimen. Okay. In unloading the specimen, you find that the limit in compression decreased. So you went into the tensile side, then in compression, the limit decreased. This is Bauschinger effect. It's a part of work hardening. But work hardening in general, we have to describe the evolution of the current elastic domain. So what people did, they tried to introduce parameters to characterize the current elastic domain as a function of the stress state and of hardening parameters to be defined. The first idea, 1931, is called isotropic hardening. It depends on one scalar hardening parameter, and it means that the yield domain will increase homothetically, as represented here. Well, we will see afterwards that this is not satisfactory. Other historical model is called kinematic hardening. For this one, we have Milan, which is German, Prager. For these three, what is it? Kinematic hardening with parameter, but it is a tensor hardening parameter. And it's easier to understand with some kind like this. Here we are. This is the initial domain, and the elastic domain remains is just translated. And the translation is governed by a rule that was given by Milan. Yeah. Well, these are historical hardening models. So now we are going to the end of this lecture, and we started with experiments. We will finish with experiments. Experiments 1969 by Bowie, Huidong Bowie, unfortunately died in, and he introduced disruptive metrological advances. He could gain more than one order of magnitude to evaluate plastic permanent strain. It could evaluate 10 to the minus 5. So this changes everything. Why? Because when you are looking for the elastic domain, you have to test every point. And to test if you find some strain, permanent strain or not. But whenever you find permanent strain, you modify the domain. So it has to be very small, very small, very small, so that you are always dealing with the same domain. Otherwise, you are changing it, and it will not converge. So it is what it did. In a given Monterey state, you have to detect new permanent strains. And these new permanent strains themselves, they modify the hardening state. So they have to be very, very small, tiny. So you have observed unexpected behavior at the early stage of work hardening. Remember the Bauschinger effect? You will see something contrary to the Bauschinger effect. In green, you have an initial boundary for aluminum, then traction, compression. And this one is shear stress. Let us increase in traction. This is a new boundary. We look here to look at the Bauschinger effect. Closer. This was initial. This is a new one. It went the wrong way. So at the very beginning, for first step, it goes the wrong way. It is anti-Bauschinger effect. Afterwards, it goes the right way. So this was the first result obtained by Bowie. The second one, it could test the actual domain, and we could test and see how it describes the evolution, if you like. For instance, here, let us have a constant sigma ZZ loading path. So we start from this point and we go up here. You see the shape? This could be considered as something like a kinematic hardening, but here, this is not kinematic hardening. You have some kind of a corner, and you can check and say, well, the normality rule is valid. Now, the same on the other side, with a radial loading path. Well, more or less the same, but here, the corner here and normality rule. So you see the shape is changed. You cannot accept either a translation or an isotropic hardening if something is changed. And these were the new results obtained at that time. So now we are at the 60s, 70s, computers are present, and there is a need for practical work hardening models to be implemented in computer codes. And those two guys made an attempt. They introduced the concept of generalized standard materials. The idea is the following. We have these are stress state. Let us assume that these are the hardening parameters. And imagine a space which is a product space, stress state, hardening parameters. And they say that the current elastic domain in that space is a convex. And that from this, you can derive the flow rule and the hardening rule through a normality rule. This is what they assumed. They started from some models, you see, and they said, well, we can assume this. See, what is interesting in this assumption, when it is acceptable, of course, is that it makes it possible to obtain existence and uniqueness theorems for the solutions, which is, of course, important when you are making computer calculations. If the solution doesn't exist, or if it is not unique, you don't know where you are going to. So it was, when it works, it was good. Well, this is not the end of the talk, but we go to the conclusion. Usually conclusion, the word conclusion means that you are closed something, but it will not be a closure. I want it to be an opening, and ask questions, and we'll try to think. These are the gallery of portraits. All the people we met, starting with Tresca, ending with Son. And by the way, it so happened that starting from this one up to this one, I was lucky enough to meet them at least once, and even to be in the same lab as some of them, Bui, Son, Anfen, to be Brezis was elected at the Academy at the same time as myself. We were introduced at the same time. So far, so good about the portraits. Let us take the two first lines. Well, the two first lines, they lead us to the 60s. That is what we may call the history of the theory, leading to what I will call the canonical form. Canonical form. We start with partial differential equations, boundary value problems, and within the mathematical context available at that time, well, they were concerned with analytical solutions, and we're doing that. Numerical methods, but very classical numerical methods such as finite differences, characteristics, something like that. Very classical numerical methods. And nobody was asking about the convergence of anything of that. This to the 60s, mid-60s, let us say. And now, last line. It's strange. Remember, we spoke about convex analysis, functional analysis, and I add here a numerical analysis. Well, we are in the 60s. There is some kind of a momentum of those studies, analysis, as I said. And in fact, they start not from equations on boundary value problems, but variational principles. Those variational principles were already available. They were available before 1940 for most of them. But you could not implement methods because you only very, very rough methods to minimization process with the variation principle. So what happened? What happened was the appearance of computers. Computers became available. I remember when I made my own thesis, starting in 1964, I was calling a computer we had a phone, we dial a number, then we are connected and could start. It was 64, it was IBM something, at the other end of Paris. Sometimes, well, it was cut because the phone line was cut, and so on. We had to do it again and again. So remember, the 60s, 1964, remember myself. But once you have computers, it changes everything. Numerical methods based upon variational principles become efficient. You can do them efficiently. And so, back, that's not now. Too early. You have not seen it. Okay, we did not see anything. So, if you have new methods, one of them, for instance, is finite element method. Finite element methods, those people, they were asking about convergence. Convergence, you have new functional spaces. You know, for instance, L-square space. You prove that the solution converges in some kind of functional space. So this is all what happened during these decades and decades. But some people did question about the physical consistency. Well, on this side, you have solutions in those mathematical spaces, functional space, L square, and so on and so on. But the data at the beginning, the data on the behavior of the material, they are not in that space. They are given at any point. The criterion should be satisfied at any point. So is it consistent? And this explains why, I said 2 or 3 decades ago, some people, one on the same lab as we, had the idea of expert systems. They say, well, we discard all those ancient approaches. We'll just do this. We have a computer, we have deep learning, we'll start from results we know from structures or elements of structures, and we go straight to the answer concerning the structure we are interested in. So this was the idea of expert systems, maybe 2 or 3 decades ago. By the way, I know that it stopped. It didn't flourish, I would say. But now, here you have seen it. Now you can see. AI is present. It is ineluctable. It is unavoidable. It will interfere in our work of today, but we don't know how. Let me tell you a story. Before leaving this is 2 weeks ago, I was at the academy and asked one of my colleagues, specialists in this AI, and said, well, I don't know how this will come in our work today. And he said, well, Jean, just ask DeepSeek or ChatGPT, just Jean Salençon, and look at the answer. And he said, the answer will be rude, will be wrong, but it will be exhaustive. I said, this guy is very smart. This must mean something. The answer is wrong, but exhaustive. And finally, I understood. It is wrong, but it is up to us to see where it is wrong, to ask the good prompts, because AI is exhaustive, it goes fast, and it can go everywhere. So this is how it will interfere with our problems. We have to be smart enough to take the right part and look deep inside to discard the wrong ones. So shall we have AI-assisted designs? Well, just some years ago here with my colleague Alain Péquer, he presented a bridge he had designed the foundations for in Greece. And he said, anytime we have to design a bridge, it's a prototype, which is true. But it so happened that his prototype was a real prototype, because 2 bridges afterwards were built with the same foundations. So it was not AI which found the foundation. It had been done. It was human mind. But imagine with AI, you could look after all bridges that had been built and find the one for which the foundation problem is exactly the same or more or less the same, and try to take the same or something or inspired solution. So this is the way it may happen. What I believe, however, is AI, of course, will impact research. It is clear. About practical applications, the problem will remain certification, legal responsibility. Once you come to a practical problem, who is responsible for that? So it has to be certified. Otherwise, the insurance will not accept it. So with this, I thank you for your kind attention.
Okay, so thank you, Professor, for your interesting talk. So let's talk now is open for discussions. So any questions from the audience, colleagues, and students?
If you have any idea about AI, what AI can do,
I think everybody took the courses about plasticity or elasticity. Any questions from the audience?
But if there are no questions, I have answers. No, what I mean that I believe that AI will help. Remember, we start from data, behavior of material, and we go to the end solution for kind of a structure or something like that. I believe that even at the very beginning, with AI, the same experiments, we will be able to find more out of them. So, due to exhaustivity. Okay. So this, I think, will be something which will happen. Afterwards, I'm not, I cannot guess what it will happen, but I think this will be.
Yeah, if the question, I would ask you a question, Professor. Okay, so when I listen to your talk, it reminds me of when I was studied at Peking University, we studied the mathematical theory, plasticity, elasticity. But when I moved to the U.S., when we study plasticity, people give a new perspective they focus on the role of defects on plasticity, like dislocations. The first question you would ask, okay, if the solid's going to flow like a liquids, something must be moving within the solids, right? So they trace the plastic back to something like defects within the material, right? So do think the continuum theory, but at the time we feel that continuum theory is excellent, okay, in terms of the mathematics. You have equations to deal with, very nice set of equations. You can use different tools to solve the equations. But when it comes to the defects, the messy picture will arise. You think that, okay, there have a bunch of dislocations moving around. So in that case, you don't have a nice mathematic framework to solve the equations. You have to rely on computer simulations, first principle calculations, right? So what's your opinion on the development of two different, I would say, this set of theories? One is physics-based, the other one is mathematics-based, right?
Yes. Well, I had to skip some, which are not here, but when I've been elaborating this lecture, there were more parts than what you have seen. And one was about, I was saying about that I had skipped damage mechanics, for instance. And what I think is that when a theory needs too many parameters to explain things, you should stop with it. You have to find another one. And if you have to find another one, you have to go back to physics. Not mathematics, not improving mathematics. Go back to physics, to what are the physical phenomena which are happening, you see. And so this is part of the answer. Second is that we have to remember always that we are dealing with models. So we should not think that nature should stick to models, but models should be appropriate for nature. This is not, if it doesn't work, this is the fault of the model, not the fault of nature. And this is something it took time for me to understand, because when I was educated at Polytechnique, we are always thinking, when it was wonderful mathematics, it should be true. And if the experiments did not prove what was not correct with the mathematics, the experience was wrong. And I remember one of my the director of the lab said, I only do one experiment, because if I were to do two, maybe it would not go. So I take only one. So he said, only one. So this is kind of thinking which we could find, for instance, in France, because we had good mathematicians. And for instance, the British have good physicists. It's a different way of thinking. I remember when I was in UK, and in 73 I was presenting something, and I remember the guy in front of me said, well, it's smart mathematics, but they were not convinced. There are people you cannot convince with mathematics. You have to convince them with your hands also. And this is very good for me when I taught in Polytechnique, for instance. I had to make those young guys who are full of mathematics, that you should understand it with your hands. I think this is important. It answers partly your question, you see. Not exactly the answer, of course, but it is the way I think it.
Right.
So, continuum mechanics is a wonderful model. It was adapted, you have seen, 1820 something, that's Cauchy. It was adapted with the mathematical context at the time. maybe we have to invent new theory adapted to our mathematical context, which is yours, not mine. Mine is soon finished. But your mathematical context, it will change.
Okay, thank you for the question. Any further question from our colleagues?
Anyway, I stay here for 1 week, so if you have
Right.
questions, you can find me here over.
Right. As the office, right? No further questions, so let's give a round of applause to Professor Chalason. Okay.
Good, thank you.
Thank you.
Thank you so much.
Thank you.